So section 10.5, trigonometry and areas, a lot like a section we did back in 10.3 when we're finding areas of regular polygons. Now we're going to be solving those questions just a little slightly differently in this section. So as a review, we can use trigonometry if we want to find the area of, again, a regular polygon, where we know the length of a side, a radius, or apothem. So we could have a few different starting points. First question, just as our example, what is the area of a regular nonagon with 10 centimeter sides? First part of this question, you need to know that a nonagon would have 9 sides, even if we didn't have a figure to count. Nonagon, again, meaning 9. And we know back from our 10.3 section that area of any regular polygon is still 1/2 the apothem length times the perimeter. First part of this question we could figure out at the very start. If I know that the sides are 10 centimeters each, and if I know a nonagon has 9 sides, I could start the question just by saying the perimeter is 10 for a side length times 9 sides, or 90 centimeters in total. So the only thing that's left is to find what's missing for the apothem. And the apothem is a lot like, again, 10.3. If I focus on not the entire shape, but just the right triangle that we can form by starting from a central angle and cutting that side in half, we should be able to figure out the pieces of that triangle in order to help us with our apothem. So focusing on, again, that right triangle, if I start with the angles in that triangle, kind of like that last section, I can start with 360 as a circle in the center. But since we're looking at a nonagon, we can break that up into 9 pieces. So 360 divided by 9 sides gives us 40 degrees for a central angle. But just like in that last section, again, we have to cut that central angle in half if we want to make that right triangle. So 40 divided by 2 means that 20 degrees is going to be at the top of one of those right triangles. So we do know one of the sides of the triangle. It's going to be 5, just because if a side length is 10, of the nonagon, since I'm breaking that side in half, I'm just using a 5 for that right triangle, meaning that if all I have to do to find the apothem is to take the tangent of 20 degrees. Because again, I can't use my special right triangle ratios. It's not a 30, 60, 90, and it's also not a 45, 45, 90. But if I know I start with an angle of 20, I still know that the opposite over adjacent ratio is going to be my tangent. So what I would do to find that apothem, and again, apothem is that length heading up from the side to the center of our figure. That apothem length is again just going to be the tangent of 20 degrees, gives us that ratio of 5 over a. So it needs to be in that order. Since we're starting at the angle, the opposite would be 5 and the adjacent would be that apothem for a. So tangent of 20 again is 5 over a because that's opposite over adjacent. If you remember back to our trig section, if my variable is ever on the bottom of that ratio, that means I can just switch places with the trig function itself. So I could say that the apothem is going to be 5 over the tangent of 20. Another way that we could do that, and I kind of crossed that out in my original work, is we could figure out that other angle also. So let's say if I use the 70 degrees that would be in the other corner, could also set up a similar question. It would just be the tangent of 70 would be a over 5 if I want to put the opposite side as the apothem. So going back to what we saw as that first answer, apothem again is 5 over the tangent of 20 degrees. We can use our calculator to find that as a decimal. That would be about 13.74. And since that was the only piece that was missing, remember we found the perimeter from earlier, 10 for a side length times 9 sides. I just have to plug that into my formula. 1/2 times the apothem times the perimeter is going to give us an area of about 618. A lot of these questions are just going to ask to round to the nearest whole number. So if you got the 0.2 off because you use different decimals in your rounding, wouldn't be as big of a part of the test. So let's try those same steps again, this time with a pentagon. So a pentagon, the only thing that's going to change is now I have 5 for the number of sides. And we also changed the side length itself, so now it's 4 inches for each side. So first of all, I know that if we're dealing with that pentagon, 4 would be the side length. If I need to find the perimeter, I could just take 4 for the side length. 5 of those sides added together is going to make 20 for a total perimeter. So in our area formula, we already know part of it. We just, again, have to figure out what the apothem length would be. And just like that last question, and just like in section 10.3, not going to focus on the whole figure. To find the apothem, we just have to make that right triangle again. So just like in the previous question, if I take the side length and cut it in half, we know one side of the triangle is going to be a length of 2, and we could figure out the angles using the same steps as before. 360, cut it into 5 sides, that's 72 degrees for a central angle, but since we're splitting that central angle in half, the angle that goes into your triangle is a 36 degrees instead of a 72. But now that I have this set up for my right triangle, if I just want to find the apothem, should be our same tangent function, because I still have the opposite and adjacent pieces. If I don't know the hypotenuse, I can always use a tangent. So again, tangent of 36 degrees, in that ratio it should be opposite over adjacent, so that's 2 over the apothem length. And just like the last question, if I have a variable on the bottom of that ratio, I can switch places with the tangent function. So the apothem is then going to be 2 over the tangent of 36, which our calculator is going to tell us as 2.75 or something like that. So now that I have those two pieces, we found the perimeter from earlier, 4 for the side length, 5 sides, 20 is the perimeter, and once I substitute in that apothem length, 1/2 of 2.75 times 20 should come out to about 27.5 square inches. And again, could round that also to the nearest whole unit, depending on what we're asked for. So let's try this again, this time using an octagon. Nice thing is that it should be pretty much the same steps. Because we are using that same formula, it's still going to be 1/2 apothem times perimeter. This time, though, we start with the length of a radius, which we didn't have in the last couple questions. Last couple questions started with a side length. If we start with the radius, it's actually going to take a little bit more work. So we're still going to do the similar steps to find the area of that stop sign. I know, first of all, that an octagon would have 8 sides. So if I did draw this whole figure, or if I look at the figure next to it, we know that the number of sides is going to end up being 8. And if I start with a radius, first of all, we'd have to know what that would look like in your figure. Remember, radius is not the apothem. It's not the length that's going straight down. The radius starts in the center, and it goes to a corner of that figure. So it goes to one of those vertices. So 16.2, once we look at that right triangle again, is going to be the hypotenuse instead of one of those two legs. So still use that as a starting point. It's still going to be important for my trig functions, but just like from before, we need to know what kind of angles we're using in that triangle also. Same steps, take 360, divide by 8 sides for an octagon, and that gives you a central angle of 45 degrees. But just like those last few questions, we're going to take that central angle and split it in half. So that's 22.5 degrees that's going into our triangle. So now that I have my triangle set up, this is really all I need to find the apothem and the perimeter. I called the apothem A again. I just listed X for that other missing side, because once we find that missing side, that's not all the work that we need for the perimeter. We're going to add in a little bit more later. But what we know to start with is that if I have this angle in the top right corner, and if I have the hypotenuse, if I want to find the apothem, that just looks like a cosine function. Remember, cosine takes the adjacent side and lists that over the hypotenuse. So if I list it in that order, cosine of 22.5 degrees is the apothem over the hypotenuse of 16.2. Only thing you have to do to find for the apothem is to multiply both sides by 16.2. So we just get the apothem is 16.2 times that cosine function. And on our calculator again, that should come out to about 14.97. Only difference is that if I'm looking for the other side length, we already found the apothem by using the cosine. If I still want to keep that same angle, 22.5, now to find the other missing side, I'll just have to use a sine function instead. Because sine function looks at the opposite side and then takes that over the hypotenuse. So we're just going to set it up that way. Sine of 22.5 degrees is going to be that other missing side length over 16.2. And once I, again, punch that into my calculator, multiply both sides by 16.2. And 16.2 times that sine value is going to give you about 6.2. Something else you could use is Pythagorean Theorem. If you already know the apothem, could do something like 16.2 squared minus that apothem squared. That would also be another way to figure out that missing leg. So now that you know the leg, you got to be careful about the perimeter. For our formula, first of all, let's go back to 1/2 apothem times perimeter. Apothem we found from earlier, that was our 14.97 answer after using the cosine. But then for the perimeter, I still have 8 sides for an octagon. But the reason why I'm using 12.4 in the formula is because when we found that missing value, that was only, again, 1/2 of a side length, meaning the entire side length, if I didn't split that side up, would be 12.4 instead of 6.2. Again, because I'd have to double that last answer. That's the side length of the octagon. So using that formula again, 1/2 times the apothem times the perimeter, 8 sides that are all 12.4. Enter that all in, should give you about 307 square inches if we're rounding to the nearest whole unit. And again, a lot of these questions will not worry about decimals. We're just going to look at the biggest whole number. So one thing we can also do is use trigonometry if we want to find area of a triangle if I know the lengths of 2 sides and the included angle. If we think back to the last semester, included means going to be the angle in between 2 sides. So we're given the formula in terms of our words, but I would just rather write it out for our area. It's going to be 1/2 of the product of the lengths, so 1/2 of B times C in this case. If I have 2 side lengths B and C that are given, I can multiply those together, divide by 2, and also I'm using the sine of the included the angle. So it can't be angle B or angle C. If I use these 2 sides for side B and side C, I would have to use the sine of the angle that's in between the two. So just like our other formulas, we could also switch up our names. We could use sides A and side C as long as I use the angle B in between. Or I could use those sides, name them A and B, as long as I use C, that's the angle in between. So just looking at this in practice, all we got to do is really some substitution. If I want to find the area of this triangle, again, I have two sides that are given and also the angle in between them. So that should be all I need. For that area, again, that's going to be 1/2 of those two sides times the sine of the angle. You just got to substitute those in. 1/2 of 12 times 21 times the sine of the angle that's included, 48. That should all just give us 93.6 if we're plugging that into the calculator. Now, one other thing is that the order is not important of the two sides that I use, kind of like our law of cosines formula that we saw from before. If I use 10 and 16, again in that formula, it could be in any order. I could do 16 times 10 or 10 times 16. As long as I'm also doing 1/2 and the sine function, so sine of 34, that's the angle in between, that should also just give us a value from the calculator. So all you're ever going to have to do on that type of question, if I start with two sides and the angle, is just substitute. 1/2 of 10 times 16, sine of 34, that should just give me a single decimal value.